When a fractured long bone bears weight, the physical forces are immense. If you apply a simple piece of flat steel to hold it together and subject it to physiological load, the construct simply fails. The screws pull out and the plate rips away from the bone. Orthopedic plates are not designed to permanently replace the structural integrity of the skeleton. Their objective is strictly temporary, to stabilize the fracture site precisely enough so that the body's natural biological healing processes can bridge the gap. This creates a direct tension between mechanics and biology. An implant cannot behave as an unyielding piece of metal. It must interact dynamically with the bone's biomechanics. In this diagram, we see the periosteum, the vascular membrane surrounding the bone. When a flat metal plate is compressed tightly against this surface to achieve mechanical grip, it chokes off the local blood supply, starving the very tissue required to form new bone. Modern orthopedic plating resolves this by engineering compromises. Surgeons carefully manipulate force vectors, precise geometric contouring, and dynamic load sharing to achieve stability without causing tissue necrosis. Understanding how surgeons repair severe fractures requires looking past the superficial resemblance to carpentry. These implants are dynamic biomechanical tools, engineered to prevent both the mechanical and biological degradation of the skeleton. The baseline model for this engineering is the dynamic compression plate, or DCP. Based on principles formulated by Martin Allgauer in 1960, it serves as the historical gold standard for treating fractures in heavy, dense long bones. In this DCP diagram, the defining feature is the oval screw holes, allowing eccentric drilling. The surgeon intentionally positions the drill bit off-center. As the screw descends, its head contacts the sloping ramp. The torque forces the plate to slide laterally across the bone. Because the other end of the plate is already securely anchored to the opposite bone fragment, this sliding motion physically drags the unanchored bone segment along with it. In this cross-section, the kinetic result becomes visible. The two broken ends of the bone are violently pulled together, creating immense pressure directly at the fracture site. For thick, healthy bones, this tight compression provides the absolute mechanical stability required for primary bone healing. It allows cells to cross the fracture gap without the disruption of micromovements. The DCP operates as an elegant mechanical converter. It takes the simple vertical torque of a screwdriver and translates it into horizontal fracture-compressing force. However, rigid compression is highly destructive if the bone in question is thin, delicate, or uniquely curved. For thin bones like the fibula, ulna, or the distal radius, surgeons rely on tubular plates, specifically the 1/3 tubular plate, which is physically thinner and slightly arched. These slender bones face a distinct stress profile. In a healing fibula, rotational instability and twisting torsional forces pose a far greater threat to the construct than simple axial load. Therefore, tubular plates act strictly as neutralization plates. Their role is to absorb those rotational forces to protect the primary lag screws, rather than applying massive horizontal compression themselves. The mechanical demands change again when treating bones with complex, sweeping geometries, such as the pelvis, or the clavicle, or the mandible. For these structural challenges, the solution is the reconstruction plate, engineered specifically for high flexibility. In this schematic, you can see how surgeons manually bend these plates across the X, Y, and Z axes simultaneously, shaping the metal in the operating room to precisely match the undulating surface of the patient's anatomy. This adheres to a strict clinical rule. The implant must be meticulously contoured to fit the bone. If a stiff plate is applied to a curved surface, tightening the screws will pull the bone fragments out of alignment. To eliminate the variable of manual bending, modern manufacturing introduced pre-contoured regional plates. The distal radius plate is a primary example of this evolution. It is manufactured to exactly mirror the complex, multi-angled topography of the wrist joint directly out of the package. Across the appendicular skeleton, anatomy dictates the geometry of the hardware. The simple application of rigid compression yields to precise neutralization and exact anatomical fit. While a perfect anatomical fit secures the fracture, an overly stiff implant introduces a biological failure known as stress shielding. In this diagram, a rigid plate takes all mechanical load. The underlying bone experiences zero stress. By Wolff's law, shielded bone rapidly weakens, turning porous. To counter this, the limited contact dynamic compression plate features scalloped undercuts, reducing direct bone contact by over 50%. This scalloped design achieves two critical biological goals. It restores blood flow to the periosteum beneath the plate, and its slightly reduced stiffness forces the healing bone to share the mechanical load. True orthopedic stability requires preserving the biological environment. The LCDCP balances the mechanical rigidity needed to hold the fracture with the vascular health required to heal it. All of these systems rely on dense, structurally sound bone. Securing weak osteoporotic bone, or complex fractures near the articular joints, presents a significantly more difficult clinical challenge. Standard friction-based screws, like those used in the traditional DCP, rely on gripping the bone tightly to generate compression. In porous, spongy bone, those threads strip and tear out, causing mechanical failure. The specific mechanical solution to this failure is the locking compression plate, or LCP. It represents a strict shift in how hardware interacts with the skeleton. In an LCP cross-section, the whole features precision internal threads. A locking screw is inserted. Its threaded head perfectly meshes with the internal threads, locking directly into the plate, not the bone. They physically act as a single, rigid, angle-stable geometric unit. Clinically, this construct acts like a fixed internal scaffold. It securely suspends weak bone fragments in place, without needing to be forcefully squeezed against the delicate periosteum to maintain stability. The locking compression plate moves the methodology entirely away from friction-dependent compression. By creating a fixed-angle biological suspension system, it solves the mechanical limits of treating severe osteoporotic fractures. Looking at the complete hardware matrix, we can see that plate selection is an exact calculation based on the distinct mechanical and biological needs of the fracture. Here, we apply dynamic compression to heavy mid-shaft bones to eliminate micromovements. We employ high three-dimensional flexibility for complex, undulating anatomy requiring geometric neutralization. And we build angle-stable internal scaffolds for fragile osteoporotic bone that cannot withstand frictional pressure. Modern orthopedics is an exercise in advanced load sharing. Every screw placement and plate contour balances the physics of stress distribution with the cellular biology of living tissue. Successful fixation goes beyond structural alignment. It is the precise engineering of a biomechanical environment that